Okay, we're now going to look at the differential mode gain for the source coupled pair. So in the circuit on the left, we have our DC biasing being achieved by the current source, I sub S. We're going to do small signal analysis, which means we eliminate all DC current sources. DC current sources are open circuited. We need to find the GM for this transistor. So really what we need to do is find the resistance looking that the source of M1 sees. Now let's go ahead and assume for the time being that we have a nearly ideal current source. So we're going to say that R sub S is approaching infinity. We're also going to say that all of the circuit is symmetric. In other words, RD1 is equal to RD2 is equal to RD. And both transistors M1 and M2 are equal to one another in size. Now, what this means is that M1 sees a resistance 1 over GM2 when connected to the source of M2. So we can say that big GM for M1 is equal to little gm1 divided by 1 plus little gm1 times 1 over gm2. Now, since these two transistors are equal to one another, their little gm's should be equal because the current flowing through them should be equal. So we can similarly say that big GM1 is equal to little gm1 divided by 2. Now, because of symmetry, we can also say that if we did this in the other direction, in other words, looked from the source of M2 towards M1, things would be the same. So we can say that big GM1 is equal to big GM2. Now, to do analysis for the differential voltage gain, we're going to use superposition. So the first thing we're going to do is put an input on V1, and we're going to short V2. We're going to put an input on VI1, and we're going to short VI2. Now, if we do this, the output voltages will be given as follows. VO1 prime would be equal to minus 1/2 GMRD, and VO2 prime is equal to plus 1/2 GMRD. This is because if we increase the voltage on the gate of M1, more current will flow through M1, reducing the voltage at the drain of M1. Because the circuit is in a symmetric operation, the reduction in the drain of M1 would have to result in an increase in the voltage at the drain of M2. This is because more current is flowing through M1 than is flowing through M2. Next, we would short VI1 and put an input on VI2. Now, the input voltage we put on VI2 is going to be the inverse of the input voltage we put on VI1 because this is a differential mode operation. So VI2 is the inverse of VI1. This means that VO1 double prime is equal to minus 1/2 GMRD. Okay, now by superposition, we're going to sum these voltages. So here we have VO1 is equal to VO1 prime plus VO1 double prime, and VO2 is equal to VO2 prime plus VO2 double prime. We can say that the output differential voltage is the difference between VO1 and VO2. In other words, VO1 minus VO2 is equal to minus GM/RD times VI1 minus VI2. The definition of our voltage gain, differential mode voltage gain, is VO1 minus VO2 divided by VI1 minus VI2. So we can say that our differential mode voltage gain, VOD over VID, is equal to minus GM/RD. In other words, this source coupled pair gives us the same voltage gain as a common source amplifier with no resistance in the source. Now, let's see if we can analyze this by symmetry. So we've already said that RD1 is equal to RD2 is equal to some value RD. In other words, the resistances are equal to one another. The transistors M1 and M2 are equal to one another. And here we're saying that RS is equal to infinity. In other words, the biasing current source is ideal. If this is the case, then we know that the source voltage V sub S is a constant. It doesn't change with respect to the input signals. So we can alternatively draw a virtual ground. If the voltage isn't changing at the source, then it's the same as it being a ground. And if this is the case, we now have a perfect symmetry, and we can draw a half-circuit model. Now, in our half-circuit model, we would assume that half of the input voltage is going into the equivalent circuit model, and half of the output voltage is coming out. Now, we know that the voltage gain for this circuit is, of course, big GM times R total. The definition of voltage gain, here we have that this would be equal to VOD divided by 2 divided by VID divided by 2, or simply VOD divided by VID. And we know the voltage gain for this simple circuit, big GM, is equal to minus little gm, and R total is approximately equal to RD. Of course, if we wanted to be more exact, we could note that the transistor also has some output resistance. All right, so interestingly, we now have two different ways to analyze a differential circuit. If we can assume symmetry, we can draw this equivalent half-circuit model. If we can't assume symmetry, then we can always rely on superposition. Either way works. The half-circuit model is much simpler for us to compute because it is a simple common source transistor amplifier. In the next video, we're going to look at the common mode gain.